This is the story of the most unsettling question in all of science. Why, in a universe containing 2 trillion galaxies and more stars than grains of sand on every beach on Earth, we have never heard a single word from anyone else? Not a signal, not a whisper, not a blip, nothing. These are the cosmic barriers, the distances, the silences, and the physics that seem almost perfectly designed to keep us alone. And this is what we actually know about why. Before we dive in, if mind-bending cosmic rabbit holes are your thing, hit the like and subscribe button. It takes 2 seconds, but it's what keeps this channel alive and the content coming. Now settle in, because things are about to get interesting. It started with a lunch. The summer of 1950, Los Alamos National Laboratory, New Mexico. Enrico Fermi was walking to the Fuller Lodge with 3 colleagues, Emil Konopinski, Edward Teller, and Herbert York. They'd been talking about flying saucers. A cartoon had just run in the New Yorker, showing little green men stealing trash cans from New York City. The scientists found it funny. The conversation drifted to faster-than-light travel, whether it was theoretically possible, how long it might take to reach the nearest stars. Teller thought the odds of seeing faster-than-light travel in the next decade were about 1 in a million. Fermi put them closer to 1 in 10. Then they sat down for lunch. The conversation moved on to something else entirely. And then, out of nowhere, Fermi blurted a question across the table. Teller remembered it as, "Don't you ever wonder where everybody is?" York heard it slightly differently. Konopinski remembered it as the shortest possible version. But where is everybody? Whatever the exact words, the table went quiet for a second, and then everyone burst out laughing. Not because the question was silly, because it was so stripped down and direct that it caught everyone off guard. The laughter came from recognition. Of course, yes, this is the actual question, and somehow no one had put it quite that plainly before. Fermi then did what Fermi always did. He started calculating. Quick, rough, back-of-the-napkin figures, the kind of estimation problems he was famous for at the University of Chicago, where he'd send students out to count piano tuners in the city. He sketched out the math. The galaxy was old. Stars like the sun had been forming for billions of years. Planets should exist around many of them. Life, if it appeared anywhere, would have had billions of years to develop, to spread, to colonize neighboring star systems. Even at modest speeds, a civilization that started 1 billion years before us would have had more than enough time to fill the entire Milky Way. And yet, nothing. No signals, no visitors, no evidence of anyone at all. Fermi never published this. He never wrote it up. He died in 1954, and the question might have faded with him, except that it wouldn't let go. Carl Sagan referenced it in print in 1963. Michael Hart formalized it in 1975. David Viewing gave it the word paradox that same year. By the 1980s, researchers were tracking down surviving participants, trying to reconstruct exactly what had been said at that lunch table. The Fermi Paradox, as it came to be known, had become one of the most discussed problems in science, born from a casual lunchtime remark that no one at the table thought much about for the rest of that afternoon. The paradox has 2 versions, and both sting. The first, why hasn't Earth already been visited? If civilizations exist out there, and if even a fraction developed spacefaring technology, the galaxy should have been colonized millions of years ago. We'd see evidence of that. We don't. The second version, why is there no signal? We've been listening with radio telescopes for more than 60 years. The universe is almost entirely silent. Both versions point at the same gap, the enormous gulf between what probability suggests should be out there and what we actually observe, which is nothing. To understand why that gap matters so much, you need to understand the numbers, and for that, you need Frank Drake. Frank Drake was born in Chicago in 1930, and by his mid-20s had become one of the most forward-thinking radio astronomers in the country. In April 1960, working at the National Radio Astronomy Observatory in Green Bank, West Virginia, he pointed an 85-foot radio telescope at 2 nearby sun-like stars, Tau Ceti and Epsilon Eridani, both within about 12 light-years of Earth, and listened. For 200 hours, Project Ozma scanned those stars for artificial radio signals. Nothing came back, but the project lit something up in the scientific community. The idea that you could systematically search for evidence of other civilizations using technology that already existed began to seem not just romantic, but genuinely scientific. A year later, J.P.T. Pearman of the National Academy of Sciences approached Drake about organizing a small conference on exactly this topic. The meeting was held at Green Bank from November 3rd to 3, 1961, and drew an extraordinary room. Philip Morrison attended. He had co-authored a landmark 1959 paper proposing that microwave radio was the ideal medium for interstellar communication. Melvin Calvin was there, and during the conference received a phone call informing him he had just won the Nobel Prize in Chemistry. At the far end of the table, the youngest person in the room, sat a 27-year-old astronomy postdoc named Carl Sagan. Drake needed an agenda. A few days before the conference began, he sat down and wrote out all the factors that would determine how many communicating civilizations might exist in the Milky Way right now. He noticed something. If you multiplied all those factors together, you got the answer directly. He had inadvertently written an equation. On the morning of November the 1st, after the guests had their coffee, Drake walked to the chalkboard and wrote N equals R star times Fp times Ne times Fl times Fi times Fc times L. That string of symbols has since been called the second most famous equation in science, after E equals mc squared. N is what they were trying to find, the number of civilizations in the Milky Way right now that could be detected. Every other term feeds into it. R star is the rate at which new stars form in the galaxy. In 1961, Drake estimated roughly 1 new star per year. Current estimates put the figure closer to 3 solar masses of new stars per year. This term is now reasonably well constrained. Fp is the fraction of those stars that have planets. Drake guessed between 20 and 50%. Modern astronomy, following the explosion of exoplanet discoveries since the mid-1990s, now estimates this fraction at close to 100%. Almost every star appears to have planets. This part of the equation has been essentially solved. Ne is the number of habitable zone planets per star. Planets close enough to their star for liquid water, but not so close that it boils away. The 2013 Kepler Space Telescope mission concluded there could be around 40 billion Earth-sized planets sitting in the habitable zones of their stars in the Milky Way alone. Not 40 million, 40 billion. Fl is the fraction of those habitable planets on which life actually arises. Here the equation runs into its first genuine wall. We know life appeared on Earth remarkably quickly, within a few 100 million years of the planet forming. But we have exactly one data point. Whether that means life is common, or whether Earth simply got very lucky, nobody can honestly say. Phi is the fraction of those life-bearing worlds where intelligence evolves. Evolution has no goals. Natural selection favors whatever traits increase reproduction in the current environment. Intelligence is metabolically expensive. The human brain, roughly 2% of body weight, consumes about 20% of the body's total energy. That investment only gets selected for under specific ecological pressures. Whether those pressures reliably arise on other worlds is unknown. Some researchers believe intelligence is an inevitable product of complex life given enough time. Others point to the fact that Earth had complex animals for more than 500 million years before anything built a radio telescope, and that the specific evolutionary path to technological intelligence involved a long chain of contingent accidents that could easily never have happened. .Fc is the fraction of intelligent species that develop detectable technology, radio transmissions, laser signals, some marker of existence. On Earth, that happened at a specific moment in the late 19th century when we began broadcasting electromagnetic radiation. Whether other intelligences would inevitably develop something equivalent is another unknown. And then there is L. L is the length of time a civilization remains in a state where it can be detected, where it's broadcasting, where it exists, where it hasn't collapsed or gone silent. Philip Morrison, sitting at that Green Bank table, had worked on the Manhattan Project. He shuddered when L came up, because he understood that technological civilizations appear to acquire the ability to destroy themselves at roughly the same moment they become detectable. If the average civilization endured only a decade before extinguishing itself, at any given moment there might be only one communicating civilization in the galaxy. One. Just us. Drake's own best estimate was that L might be around 10,000 years, giving perhaps 10,000 civilizations scattered across the Milky Way. The conference ended with champagne. Otto Struve, the director of the Green Bank Observatory, raised a glass and offered a toast. To the value of L, may it prove to be a very large number. The equation's outcomes range from exactly one civilization, us, alone, to hundreds of millions scattered throughout the galaxy. The range is so vast it's almost useless as a prediction tool, but it does something more important than predict. It shows you exactly where the uncertainty lives, and which questions, if answered, would change everything. Now, the equation can only be understood against the arena it operates in, and the arena is incomprehensible. Let's try anyway. The nearest star to our Sun is Proxima Centauri, at a distance of 4.24 light-years. A light-year is the distance light travels in 1 year, moving at 186,000 miles per second. If you drove a car at highway speed, 70 miles per hour, no stops, it would take roughly 37 million years to cover a single light-year. To reach Proxima Centauri by car would take about 156 million years. For context, 156 million years ago, dinosaurs were in the middle of the Jurassic period and flowering plants had not yet appeared. And Proxima Centauri is the closest one, our next-door neighbor in galactic terms. The fastest spacecraft humanity has ever launched was the New Horizons probe, which reached roughly 36,000 miles per hour at its peak. At that speed, reaching Proxima Centauri would take approximately 78,000 years. Our oldest cave paintings are about 40,000 years old. The entire span of recorded human civilization covers roughly 5,000 years. A journey to our nearest stellar neighbor, at the fastest speed we've ever achieved, would take 15 times the full span of human civilization. The Milky Way galaxy is roughly 100,000 light-years across and contains somewhere between 100 billion and 400 billion stars. The observable universe, the portion from which light has had time to reach us since the Big Bang, stretches approximately 93 billion light-years across and contains an estimated 2 trillion galaxies. The number of stars in the observable universe is approximately 10 to the power of 24, a 1 followed by 24 zeros. There are more stars in the observable universe than grains of sand on every beach on Earth, by a factor of over 1 million. The scale defeats intuition. Our minds evolved to track predators across a savanna, to navigate a forest, to recognize faces at close range. They did not evolve to comprehend 93 billion light-years, or numbers with 24 zeros. And this is where the Fermi Paradox becomes so sharp. If even a tiny fraction of those 10 sextillion stars host planets, and if even a tiny fraction of those planets host life, and if even a small fraction of that life develops intelligence, the universe should be teeming with civilizations. The math says there should be others, many others. But the same incomprehensible vastness that makes life seem statistically inevitable also makes contact seem physically impossible. The universe may be full of life, and that life may be as effectively isolated as if it were the only life in existence. Because the distances between stars are so enormous, and because nothing can travel faster than light, the practical separations between civilizations might be so extreme that no two of them ever manage to reach each other, or even hear each other, within their natural lifespans. In 1905, Albert Einstein's special theory of relativity established a speed limit for the universe. Nothing with mass can travel at the speed of light, and nothing at all can exceed it. The closer you get to the speed of light, the more energy you need to accelerate further, and the required energy approaches infinity as you approach the limit. Reaching exactly the speed of light would require infinite energy. This is not a technological limitation that better engineering will solve. It is written into the structure of space-time itself. What does this mean in practice? A signal traveling at light speed takes 4.24 years to reach Proxima Centauri. If a civilization around Proxima Centauri sent us a radio message today, the earliest we could receive it would be in 2030. If we replied, they couldn't receive our answer until 2034. A single exchange takes more than 8 years. The center of the Milky Way is roughly 26,000 light-years away. A message sent from there today wouldn't arrive at Earth until the year 27,026. Civilizations on the other side of the galaxy might as well exist in a different reality entirely. And physical travel is even less promising. Even a spacecraft accelerated to 10% of the speed of light far beyond anything we can currently conceive of building, would take 42 years to reach Proxima Centauri. The galactic center would require 260,000 years of travel. At those timescales, the civilization that launched the ship would be unrecognizable or extinct before the ship arrived. So the universe has installed a hard speed limit. Applied to distances that are almost incomprehensibly vast, it creates a situation where even neighboring star systems are effectively isolated from each other on any human-relevant timescale. There is another temporal barrier that rarely gets discussed as prominently as the distances. It has to do with when we exist. The universe is 13.8 billion years old. The Big Bang happened 13.8 billion years ago, and over the first few 100 million years, the first stars formed from hydrogen and helium. Those first stars were enormous, violent, and short-lived. They burned hot and fast, and exploded in supernovae, seeding the universe with heavier elements: carbon, oxygen, nitrogen, iron. The raw material for chemistry, complex enough to support life. But those first stars probably couldn't host life. Their planets, if they formed at all, would have lacked the chemical richness that biology requires. Life needs heavy elements, what astronomers call metallicity, and the universe needed several generations of stellar birth and death to build that up. By the time conditions were right for Earth-like planets, roughly 9 billion years had passed since the Big Bang. Our solar system formed 4.6 billion years ago. Life appeared somewhere between 3.5 and 4 billion years ago. Complex multicellular life didn't appear until about 600 million years ago, after more than 3 billion years of Earth being inhabited exclusively by single-celled organisms. Anatomically modern humans have existed for about 300,000 years, with technological civilization occupying the last few thousand years of that span. If you compress Earth's 4.6 billion year history into a single calendar year, life appears in February. It stays microbial for roughly 8 months. Multicellular life appears in November. The extinction of the dinosaurs happens around December 26. Homo sapiens appear around 11 p.m. on December 31st. All of recorded human history, every civilization, every war, every invention, every work of art, happens in the last 10 seconds of that year. This timeline has an interesting implication. If conditions for life became available around 9 billion years ago, and our solar system is 4.6 billion years old, there were already 4.4 billion years during which other star systems could have been forming planets and developing life before our sun even ignited. A civilization that began 4 billion years ago would have had more time to develop than the current age of Earth. In the time since that civilization could theoretically have emerged, Earth hadn't even finished forming yet. And yet, nothing has visited, nothing has called. In 1996, an economist named Robin Hanson posted an essay online with a deceptively simple title, "The Great Filter, Are We Almost Past It?" Hanson was a professor at George Mason University, not an astronomer, but he had been thinking carefully about the Fermi Paradox, and he formalized an idea that sits at its center. The argument goes like this: the universe is old and large, and full of stars and planets. Life should arise somewhere. Intelligence should develop. Civilizations should expand. But the universe, as we observe it, appears almost entirely dead. No visible civilizations, no detectable signals, no evidence of expansion. Something is stopping the chain. Whatever that something is, Hanson called it the Great Filter. It's a barrier in the sequence from lifeless matter to galaxy-colonizing civilization, a step that almost nothing makes it through. The filter exists. It has to exist. Otherwise we'd see others. The question that makes this idea so viscerally unsettling is where the filter sits relative to us. Is it behind us or ahead? If the Great Filter is behind us, if the barrier is something like the origin of life from chemistry, or the development of complex eukaryotic cells, or the emergence of multicellular animals, then we're on the right side of it. We got through. The filter exists. It's real. It's why the universe appears empty, and we were among the vanishingly rare survivors. This is actually good news for us specifically, even if it's bleak news for the overall abundance of life in the cosmos. In fact, the transition from simple prokaryotic cells to complex eukaryotic cells cells with nuclei, with mitochondria, with organized internal structure, took about 2 billion years on Earth. 2 billion years of life stuck at the level of simple single-celled organisms. Many researchers consider that specific transition as a strong candidate for where the filter lies. It took an extraordinarily long time, which might suggest it's extraordinarily difficult to achieve. But here is where it gets dark. The filter might lie ahead. If the development of life, intelligence, and technology are all not particularly rare, if they happen reasonably often, then the filter must lie somewhere between where we are now and the galaxy-spanning civilization stage that we don't observe. Something destroys civilizations after they reach our level, reliably, almost universally, something that we have not yet encountered but will. Nuclear weapons, climate change, engineered pathogens, artificial intelligence that outgrows its creators, some catastrophe we haven't yet imagined. This is why the discovery of life elsewhere in the universe would be, in some ways, deeply alarming news. If we found microbial life on Mars, the initial reaction might be celebration, but Hansen's framework inverts that reaction. If simple life is common, the great filter is probably not in the early stages of biology. It's ahead. If we found evidence of past civilizations, ruins, artifacts, dead broadcasts, that would be the most alarming discovery in human history, because it would mean civilizations can get that far and still not survive. The silence of the universe, in this interpretation, is not just a puzzle. It might be the most important survival signal we'll ever receive. In 2000, University of Washington paleontologist Peter Ward and astrobiologist Joe Brownlee published a book called Rare Earth: Why Complex Life is Uncommon in the Universe. Their argument runs against the intuition that if the universe is this large, complex life must be everywhere. Ward and Brownlee made the case that complex life, not just microbes, but organisms with nervous systems, with mobility, with evolutionary innovation over hundreds of millions of years, requires a very specific set of conditions that coincide only rarely. Consider what had to align for Earth to become what it is. Earth sits in the habitable zone of a G-type main-sequence star, the Sun, unusually stable for its type. It doesn't flare dramatically. Its energy output has increased by only about 30% over 4.5 billion years, a remarkably steady performance that gave Earth time to develop and sustain life without periodic sterilizing events. Earth has plate tectonics. Mars doesn't have active plate tectonics. Venus doesn't. Tectonic cycling serves as a planetary thermostat, recycling carbon dioxide from the atmosphere through the interior and back out through volcanoes, regulating the greenhouse effect over geological timescales and keeping temperatures within the range liquid water requires. Without plate tectonics, Venus evolved into a planet with surface temperatures above 450 degrees Celsius, hot enough to melt lead. Earth has a large moon, whose size relative to Earth is unusual in the solar system. That moon stabilizes Earth's axial tilt, currently about 23.5 degrees. Without the gravitational anchor of the moon, Earth's tilt could wander wildly over millions of years, creating climatic instabilities that would make complex life very difficult. Mars, without a large stabilizing moon, does experience significant wobbles in its axial tilt over millions of years. Earth has a magnetic field generated by the movement of molten iron in its outer core. That field deflects most of the charged particles streaming from the Sun, the solar wind, that would otherwise strip away the atmosphere and bombard the surface with radiation. Mars lost its magnetic field billions of years ago, and its atmosphere has been gradually stripped away ever since. Earth orbits in a solar system that contains Jupiter. Jupiter's enormous mass deflects or captures many of the asteroids and comets that would otherwise threaten the inner planets. Without Jupiter, Earth might face extinction-level impacts far more often, potentially not allowing enough time between events for complex life to evolve. Earth sits in what astronomers call the galactic habitable zone, far enough from the chaotic, radiation-intense galactic center to avoid frequent sterilizing events, but close enough to star-forming regions that heavy elements have accumulated in sufficient quantities. The galactic center is a crowded, violent place. Gamma-ray bursts, the most powerful explosions in the universe, could sterilize life on any planet within several thousand light-years. Our position in the outer third of the galaxy, in a relatively quiet region called the Orion Arm, is a relatively safe address in cosmic terms. Every one of these conditions, the stable star, the plate tectonics, the large moon, the magnetic field, the gas giant shield, the galactic address, had to coincide. Ward and Brownlee's argument is that the probability of all of them coinciding is low enough to make complex life genuinely rare, even in a universe with 10 sextillion stars. Now back to the silence itself, not the theoretical reasons for it, but the actual observational fact of it. For more than 6 decades, humans have been pointing radio telescopes at the sky and listening. The result has been almost complete silence. Frank Drake's Project Ozma in 1960 was the first systematic attempt. Using an 85-foot radio telescope, Drake observed 2 nearby stars for 200 hours total. Nothing was detected, but the search had begun. The assumption driving most searches was logical. Any civilization advanced enough to broadcast signals would probably find radio waves as useful as we do. The most natural frequency for an interstellar beacon, researchers reasoned, would be near the 1420 MHz hydrogen line, the frequency at which hydrogen atoms, the most abundant element in the universe, naturally emit radio waves. Any technologically sophisticated civilization would know about the hydrogen line. It seemed like the obvious place to listen. On August 15, 1977, something happened that is still not fully explained. The Ohio State University Radio Observatory in Delaware, Ohio, operated a telescope called the Big Ear. It was not glamorous, built partly by volunteers on a shoestring budget, but starting in 1973, it had been dedicated entirely to the SETI search. On August 15 at approximately 10:16 in the evening, the Big Ear detected something extraordinary. In a single frequency channel close to the hydrogen line at 11420.456 MHz, the signal jumped. Where background noise registered as 1 or 2, the reading climbed to levels the computer coded as letters because the numbers weren't enough. The sequence read 6EQJ5. A volunteer astronomer named Jerry Eman was reviewing the printed data a few days later. He circled the sequence in red ink and wrote one word in the margin: "Wow." The wow signal lasted exactly 72 seconds, the amount of time the Big Ear's fixed beam would take to sweep past a fixed point in the sky as Earth rotated. It rose, peaked, and fell in exactly the pattern you'd expect from a real celestial source. It came from the direction of the constellation Sagittarius. It broadcast at a frequency extremely close to the hydrogen line. By every technical measure available, it looked exactly like what a signal from an extraterrestrial civilization would look like. The observatory attempted to confirm the signal on subsequent nights, observing the same patch of sky. Nothing came back. The signal never repeated. In the decades since, researchers have trained multiple professional telescopes at that region of the sky repeatedly. No one has ever detected it again. Eman himself grew increasingly cautious in later years about what the signal meant. He noted that a genuine interstellar signal would be expected to repeat, or at least to be detectable on follow-up. The failure to hear it again made him hesitant to claim it proved anything, but no purely terrestrial explanation has fully accounted for all of its characteristics. And so it sits in the record, 72 seconds of something that matched everything a radio signal from another civilization would look like, and then nothing, never heard again. The history of SETI after 1977 is a history of increasingly powerful searches, finding increasingly deep silence. Computing power has expanded enormously. Sensitivity of modern radio telescopes dwarfs what was available in the early years. And still, after more than 60 years of listening, the universe remains quiet at frequencies where, if the optimistic reading of the Drake equation were correct, we should be hearing a noisy chorus. Big Ear ran its SETI program for 24 years, from 1973 until it was demolished in 1997 to make way for a golf course. And in that entire run, the only candidate signal of any significance was those 72 seconds in August 1977. SETI at Home, which recruited volunteers to run signal analysis on personal computers, ran for 21 years, from 1999 to 2020. And found nothing conclusive. Project Phoenix, searched nearly 1,000 sun-like stars from 1995 to 2004 and detected nothing. The Breakthrough Listen initiative, funded from 2016 with a stated 10-year budget of $100 million, donated by billionaire Yuri Milner, using major telescopes, including the Green Bank Telescope and the Parkes Observatory in Australia, has so far reported no confirmed extraterrestrial signals. The silence is not for lack of trying. Let us consider the self-destruction explanation, because it sits at the uncomfortable intersection of the Great Filter and everything we know about our own civilization. The idea is straightforward. Technological civilizations develop, and in developing, they inevitably create tools capable of destroying themselves. Nuclear weapons appeared in 1945, less than 70 years after the first practical light bulb. The gap between "we have basic electricity" and "we have weapons capable of ending our civilization" turned out to be surprisingly short. At the height of the Cold War, the United States and Soviet Union together possessed tens of thousands of nuclear warheads. The doomsday clock, maintained by the Bulletin of the Atomic Scientists as a symbolic measure of how close humanity is to catastrophe, was set at 2 minutes to midnight in 1953, after both superpowers tested thermonuclear bombs within 9 months of each other. The risk of nuclear exchange during the Cold War was far greater than is generally acknowledged in retrospect. Multiple declassified incidents reveal how close the world came. In October 1962, the Cuban Missile Crisis brought the superpowers to the edge. A Soviet submarine near Cuba, under depth-charge attack and cut off from communication with Moscow, carried nuclear torpedoes and authority to use them. The decision not to launch rested on one officer, Vasily Arkhipov, who refused to give the required second officer authorization to fire. One individual's judgment may have prevented a nuclear exchange. In September 1983, a Soviet early warning satellite reported 5 incoming American intercontinental ballistic missiles. Duty officer Stanislav Petrov was supposed to report the launch warning up the chain of command, which would have triggered retaliatory protocols. Instead, he judged, correctly, that the alarm was a malfunction because a real first strike would have involved hundreds of missiles, not 5. He was right. He was also, by his own account, frightened and uncertain, making a judgment call under enormous time pressure without enough information. These are not anomalies. Declassified documents reveal a substantial catalogue of close calls, misidentifications, and equipment failures throughout the Cold War. The fact that nuclear war did not occur was partly good judgment by specific individuals at specific moments, and partly luck. Philip Morrison understood this from the beginning. At the Green Bank Conference in 1961, he had worked on the Manhattan Project. He had witnessed the first atomic bomb. He shuddered when the question of L came up, because he understood that the moment a civilization becomes powerful enough to be heard across interstellar distances is roughly the same moment it gains the ability to silence itself. From the perspective of the Drake equation, what matters is whether civilizations reliably navigate this zone of maximum danger. The evidence from Earth suggests that the period between radio telescopes and nuclear reactors and self-sustaining interstellar civilization is a very tight window of extreme vulnerability. If most civilizations fail to navigate that window, the universe would look exactly as it does: occasional brief flickers of radio noise, and then silence. Now we arrive at what might be the most psychologically disturbing resolution to the Fermi Paradox. Not that contact is impossible, or that civilizations die, but that contact is deliberately avoided. In 2008, the Chinese science fiction author Liu Cixin published a novel called The Three-Body Problem, and its sequel, The Dark Forest. In The Dark Forest, Liu articulated a hypothesis that carries the structure of a genuine logical argument. The argument begins with 2 premises. First, survival is the primary need of every civilization. Second, civilizations continuously expand, and the total matter in the universe remains constant, meaning civilizations will eventually compete for finite resources. From these 2 premises, a terrifying logic follows. If Civilization A detects Civilization B, Civilization A cannot know whether Civilization B is friendly. It cannot communicate quickly enough across interstellar distances to determine intentions before the consequences of a wrong assumption become fatal. The rational strategy, under these conditions, is to eliminate any other civilization detected before it can do the same, and to do so without announcement, without revealing your own location. The universe, under this theory, is not empty. It is full of civilizations crouching in the dark, watching, staying silent, eliminating any source of detection as quickly as possible, because in the dark forest of the cosmos, any sound can draw a predator. There is something genuinely chilling about this theory, even setting aside its fictional origins, because the logic is not actually wrong. The premises are reasonable extrapolations from what we know about survival and resource competition. The conclusion that the rational response to detecting a signal might be to send a weapon rather than a greeting is uncomfortable but coherent. The dark forest theory carries a secondary implication for SETI. The signals we're looking for might not exist, not because civilization is rare, but because civilized beings learn very quickly to stop broadcasting. The first civilization to transmit openly might be the last. Every other civilization, observing the silence of its predecessors, draws the obvious conclusion and goes dark. This would explain everything. The silence is not absence, it is caution on a cosmic scale. There are serious objections. The theory assumes resource competition will remain a driver of conflict, even for civilizations that have presumably solved their local energy and resource problems. And it assumes that civilizations would strike first without attempting communication, which requires a certain baseline paranoia. A civilization that survived its own technological adolescence might have done so by developing cooperation as a strategy, in which case its assumptions about other civilizations' intentions would look quite different. But as an explanation for why an inhabited universe might look like an empty one, the dark forest theory has a completeness that is hard to dismiss. It requires no physical barriers, no rare conditions, no great filter ahead, just rationality in the dark. In 2003, philosopher Nick Bostrom at the University of Oxford published a paper titled, "Are You Living in a Computer Simulation?" The paper argues that at least one of three things must be true. Civilizations go extinct before reaching the capability to run sophisticated simulations, or civilizations at that level don't run such simulations, or we are almost certainly living in a simulation. The argument has attracted serious engagement from physicists and philosophers. The relevance to the Fermi Paradox is indirect but interesting. If the observable universe is a simulation, the absence of other intelligent life might be an intentional feature of its design. The universe might appear empty because the simulators chose not to populate it with other civilizations. This is not science in the traditional sense. It's not testable or falsifiable in any obvious way, but it occupies a strange corner of the logical space of possible explanations, and it remains philosophically coherent. On December 25, 2021, the James Webb Space Telescope was launched from French Guiana. It is the most powerful space telescope ever built, with a primary mirror 6.5 meters in diameter, nearly 3 times the diameter of the Hubble Space Telescope. Webb observes primarily in the infrared spectrum, which allows it to peer through dust clouds and detect the chemical signatures of planetary atmospheres across enormous distances. One of its primary scientific objectives is to characterize the atmospheres of exoplanets and search for biosignatures, chemical compounds whose presence in a planetary atmosphere would suggest biological processes. Oxygen, methane, water vapor in combinations that don't occur through purely geological processes. Ozone, all of these could potentially be detected by Webb given the right circumstances. Modern exoplanet surveys based on Kepler data have catalogued thousands of confirmed exoplanets and established that Earth-sized planets in habitable zones are common. The estimate of 40 billion such planets in our galaxy remains one of the most striking numbers in modern astronomy. Not 40 million, 40 billion, and still the silence. Pull all of this back together, because each thread is part of the same answer to Fermi's question. The universe is 13.8 billion years old and contains something like 10 sextillion stars. The probability that life has arisen elsewhere is difficult to make small without invoking conditions that seem almost deliberately contrived. And yet the observable universe shows no sign of other technological civilizations, no signals, no megastructures, no expanding wavefronts of colonization, no evidence of any kind. The explanations range across a spectrum of hope and dread. Maybe the rare Earth hypothesis is right, and complex life is genuinely uncommon. We are a statistical miracle in a largely sterile cosmos. Maybe the great filter is behind us, and we passed through something extremely improbable to reach this point, and the rest of the universe is full of bacteria and nothing more. Maybe the distances are simply too great for any civilization to bridge on relevant timescales, and everyone is isolated in their own tiny bubble of dark, listening to silence and assuming they're alone. Maybe civilizations routinely self-destruct through the weapons they build, and the silence is what a civilization's last radio transmission sounds like from several thousand light-years away. Maybe the cosmic dark forest is real, and everyone learned long ago that broadcasting is suicidal. Maybe the filter is still ahead, waiting for us at some threshold we haven't yet crossed. And maybe, sitting 4.24 light-years away around the red dwarf star Proxima Centauri, or somewhere among the billions of habitable zone planets catalogued by Kepler, or in some star system whose atmosphere the James Webb Space Telescope will examine in the coming years, maybe somewhere out there, life is looking up at its own night sky, running its own version of Fermi's arithmetic, and arriving at the same bewildered silence. The question Fermi blurted across that lunch table in New Mexico in the summer of 1950 has only deepened in the decades since. Not because we've found no answers, but because every answer we've found points back at a universe that seems, for reasons we still don't fully understand, almost perfectly structured to keep its inhabitants separate from each other, by distance, by time, by physics, by catastrophe, by caution, or by some filter so improbable that you can spend a career staring at it and still not see exactly where it sits. There are 2 trillion galaxies out there. Somewhere between them, Enrico Fermi's question is still waiting for an answer. And the universe, so far, is not talking. Now, to truly understand why the silence persists, you have to understand what the universe actually is in physical terms. Because the universe is not a gentle, life-permitting place that happens to be vast. It is a violent, radiation-soaked, thermodynamically hostile environment in which the survival of complex chemistry is the exception rather than the rule. Start with gamma-ray bursts, the most energetic explosions known to occur in the universe. When a massive star collapses at the end of its life and forms a neutron star or black hole, or when 2 neutron stars spiral into each other and merge, the result can be a burst of gamma radiation so intense that it briefly outshines an entire galaxy. These events emit, in seconds or minutes, more energy than the Sun will produce over its entire 10 billion-year lifespan, directed in a tightly focused beam punching through space in 2 opposite directions. If a gamma-ray burst were to fire within a few thousand light-years of Earth and its beam were pointed in our direction, the pulse of radiation would strip away the ozone layer within seconds. Without the ozone layer, ultraviolet radiation from the Sun would reach the surface unchecked. The effect on photosynthesis would be catastrophic, collapsing food chains from the bottom up. Some researchers have proposed that a gamma-ray burst may have been responsible for the Ordovician-Silurian extinction event, approximately 445 million years ago, which wiped out roughly 85% of marine species. This remains a hypothesis, but it illustrates the plausibility of the mechanism. Gamma-ray bursts appear to occur approximately once per day somewhere in the observable universe, most at cosmological distances and posing no threat. But in a galaxy with hundreds of billions of stars and a history spanning 10 billion years, the probability that any given planetary system has experienced a nearby burst at some point in its history is not negligible. In the early universe, when star formation rates were much higher and massive short-lived stars were more common, gamma-ray bursts would have been more frequent and the galactic environment more hostile. Beyond gamma-ray bursts, ordinary supernovae pose a more common but lower intensity risk. A supernova within about 25 to 30 light-years of Earth could deliver enough radiation to cause significant ozone depletion. Supernovae happen in our galaxy at a rate of roughly 1 to 3 per century. Over billions of years, the cumulative radiation bombardment of the galaxy is enormous. Any planetary system in a dense stellar neighborhood faces a substantially higher rate of sterilizing events than our relatively quiet address in the Orion arm of the Milky Way. This environmental hostility directly shapes the answer to Fermi's question. The universe doesn't need to produce no life anywhere for the paradox to be explained. It only needs to produce life rarely enough, in conditions good enough to sustain it over billions of years, in locations safe enough for it to persist and develop complexity. When you inventory all the ways the universe actively works against that, the intersection of required conditions starts to look less like a near certainty and more like a very lucky accident. There is a step in the Drake equation that receives less attention than the others, and may be the most important one. It is phi, the fraction of life-bearing worlds where intelligence evolves. This variable carries an assumption so embedded in how we think about evolution that we rarely notice it. The assumption that intelligence is a direction evolution moves toward. That if you give biology enough time, minds will eventually appear. This feels intuitive because we are the product of it. But the fossil record suggests something more complicated. Evolution has no goals. Natural selection is a blind process that favors whatever traits increase an organism's ability to reproduce in its current environment. Intelligence is metabolically expensive. For it to be selected for, it has to confer survival advantages powerful enough to offset its costs. On Earth, that payoff materialized through a specific combination of ecological pressures: group living, complex social hierarchies, tool use, the demands of coordinating behavior across large social groups. But the path was not inevitable. The lineage that produced humans is one branch in an extraordinarily bushy evolutionary tree. Life existed on Earth for more than 3 billion years before anything recognizably on a trajectory toward telescope building arrived. The specific lineage leading to humans required a series of contingent events. The extinction of the non-avian dinosaurs 66 million years ago, caused by an asteroid or comet roughly 10 kilometers in diameter striking the Yucatan Peninsula, cleared the ecological stage for the rapid diversification of mammals. Without that impact, the evolutionary dominance of reptilian forms might have continued indefinitely, with mammals remaining small, nocturnal insectivores. The intelligence that built radio telescopes might never have found the evolutionary space to develop. Stephen Jay Gould's Replay the Tape thought experiment remains one of the most powerful challenges to the idea that intelligence is an inevitable product of evolution. If you reset life on Earth 600 million years ago and ran it forward again, the result would almost certainly be something entirely different. Not because evolution is random in any simplistic sense, but because the contingent events that shape evolutionary history would unfold differently. A planet could be teeming with intelligent life, intelligent by almost any standard we'd apply, and still produce no civilization in the technological sense. Dolphins have been present on Earth for tens of millions of years. They have large brains, complex social lives, apparent emotional depth, and demonstrable problem-solving ability. They have never built a radio telescope, not because they couldn't eventually have gotten there given enough time, but because the specific environmental pressures and physical equipment required haven't converged in the right way. For most of human history, the planets in our solar system were the only planets we knew existed. The actual observational confirmation of planets around other stars was a long time coming, and when it arrived, it rewrote the Drake equation in real time. The first confirmed detection of a planet orbiting a main sequence star came in 1995, when Swiss astronomers Michel Mayor and Didier Queloz announced the discovery of 51 Pegasi b, a gas giant orbiting a star roughly 50 light-years away, in just 4.2 days. It was detected using the radial velocity method. As the planet orbits its star, its gravity tugs the star slightly, causing a periodic Doppler shift in the wavelengths of the star's light. Mayor and Queloz received the Nobel Prize in Physics in 2019 for this discovery. Within a few years, the method had found dozens of exoplanets, almost all of them hot Jupiters, simply because the method is most sensitive to large planets in close orbits. The Kepler Space Telescope, launched in March 2009, changed everything. Kepler monitored approximately 150,000 stars continuously for 4 years, looking for the tiny periodic dips in brightness when a planet passes in front of its star. The results were astonishing. Kepler found thousands of confirmed exoplanets and revealed that the galaxy is extraordinarily full of planets. Small, rocky planets are among the most common types detected, and Earth-sized planets in the habitable zones of their stars occur around a significant fraction of Sun-like stars, roughly 22% by the best current estimates. Applied to the Milky Way's roughly 100 to 400 billion stars, the calculation suggests somewhere between 1.5 to 10 billion potentially habitable Earth-sized planets in our galaxy, orbiting Sun-like stars alone. The 40 billion figure for all stellar types has become one of the most frequently cited statistics in astrobiology, not because it's precise, but because it illustrates the sheer scale of the opportunity. Among the most interesting individual worlds discovered since Kepler is Proxima Centauri b, announced in 2016, and orbiting our nearest stellar neighbor at a distance, placing it within the habitable zone. The fact that even our nearest neighbor apparently has a potentially habitable planet is striking. It suggests that such planets are indeed common throughout the galaxy, not clustered in specific regions. The Kepler mission's legacy is that it transformed the second and third terms in the Drake equation from vague hope into statistically constrained numbers. We no longer have to guess whether planets are common around other stars. We know they are. The question that remains is what those planets are like, whether they have atmospheres, whether those atmospheres support liquid water, and whether they harbor life. For much of the 6 decades since Project Ozma, the SETI enterprise has faced a fundamental problem of public credibility. Not because the science was bad, but because the culture surrounding unidentified aerial phenomena generated associations that serious researchers found damaging. The critical distinction is methodological. SETI research is conducted using calibrated instruments, statistical methods, independent verification, and peer review. The bar for announcing a detection is intentionally very high. The UAP phenomenon involves reports of unexplained observations, often from military sensor systems not designed for scientific measurement, in conditions that make rigorous analysis difficult, with chain of evidence problems that prevent scientific verification. In 1993, the US Congress specifically cut funding for NASA's SETI program, the High-Resolution Microwave Survey, with Nevada Senator Richard Bryan attaching an amendment to a budget bill that terminated the program, calling it a waste of taxpayer money. The program, which had cost approximately $12 million over its life, was dead before it had truly begun. The institutional memory of that congressional intervention made NASA cautious about funding explicitly SETI-labeled projects in the years since. Private funding has sustained most SETI research. The Allen Telescope Array, funded by a donation from Microsoft co-founder Paul Allen, and the Breakthrough Listen initiative, funded by Yuri Milner. Private funding is more volatile than sustained government investment, and the allocation of resources has been limited by what individual philanthropists choose to fund, rather than by a systematic national assessment of scientific priorities. The asymmetry argument for better funding is straightforward. A detection, even a single confirmed signal from another civilization, would be the most transformative discovery in human history, affecting every dimension of human culture, philosophy, religion, science, and self-understanding. The cost of not looking, if a signal exists and goes undetected because we weren't listening with adequate sensitivity, is incalculable. The question, where is everybody, is not only a scientific question, it is a question about meaning and identity on a cosmic scale. The answer matters not just for what it tells us about biology or physics, but for what it tells us about ourselves, about the significance of human existence, about the nature of consciousness in the universe, about whether the qualities we most prize about ourselves have any counterpart anywhere else. If we are alone, if the great filter is behind us and Earth is the only living world in the observable universe, then the implications are almost too large to hold. Every piece of music ever written, every work of art, every moment of human understanding, every story and love and grief, all of it would be the only such thing in a universe 93 billion light-years across. Not merely rare, unique. The entire 13.8 billion-year history of the cosmos, with its 2 trillion galaxies and 10 sextillion stars, would have produced exactly one world capable of wondering about itself, and we would be it. That is not necessarily a reason for despair. Some researchers find it a source of immense responsibility, and even a kind of awe. If consciousness has arisen only here, then the universe's capacity for self-awareness, for beauty, for knowledge, resides entirely in us. The weight of that, to understand, to preserve, to continue, becomes correspondingly enormous. If we are not alone, if others exist, scattered across the galaxy and beyond, living and thinking and perhaps wondering the same things, then the silence becomes a different kind of existential challenge. We are not unique, but we are isolated. Connection is possible in principle, but unreachable in practice. The fellowship of minds that the optimistic Drake equation implies exists, but the universe has arranged things so that we can never actually meet. This might be the most melancholy version of the answer, that intelligence is scattered across the cosmos, that other beings look at their own night skies with the same mixture of wonder and loneliness, and that the physical structure of the universe, its vast, light-speed limited distances, its billions of years of development required for complexity, its finite civilizational lifespans, conspires to keep every conscious thing perfectly and completely alone. The Fermi Paradox has two deeply unsettling resolutions, and both demand a kind of civilizational maturity that humanity may not yet have developed. If the answer is that we are alone, the implication is a weight of cosmic responsibility that our civilization is poorly equipped to bear. The entire project of building a long-term, sustainable, peaceful civilization, of learning to cooperate globally, of avoiding the catastrophes that our own weapons and technologies make possible, would acquire a new kind of urgency. Not because humanity is intrinsically important in some cosmic hierarchy, but because, if we are the only mind in the observable universe, the universe's capacity for self-awareness can be lost, permanently and irrecoverably, if we fail. Our civilization does not currently behave as though it feels this weight. We build weapons capable of ending ourselves, deploy them in unstable geopolitical contexts, change our climate without coordinated global response, and fail to maintain the institutional frameworks for international cooperation that a civilization aware of its unique status might reasonably prioritize. This is not necessarily because we're uniquely foolish. It may be because we evolved for a very different scale of community and a very different pace of change. But the mismatch between our evolved psychology and the challenges we face is real. If the answer is instead that others exist but something stops them, that the great filter lies ahead, and that the silence is a warning about what destroys civilizations at our stage of development, then the implication is even more directly actionable. It suggests that the specific risks we face right now, in the early 21st century, are the risks that filter civilizations: nuclear weapons, climate change, engineered pathogens, misaligned artificial intelligence, political fragmentation at the moment of maximum technological power. These are not speculative future risks. They are present realities that our civilization is actively and imperfectly managing. The Fermi Paradox, in this reading, is not just a scientific puzzle about the distribution of intelligence in the universe. It is a message, written in the silence, about what happens to civilizations that don't get this right. The Square Kilometre Array, or SKA, currently under construction in South Africa and Australia, is the next major leap in radio telescope capability. The SKA is not a single dish, but an array of thousands of antennas spread across 2 continents, whose signals are combined digitally to produce the equivalent sensitivity of a dish with a collecting area of 1 square kilometre. When fully operational, the SKA will be orders of magnitude more sensitive than any previous radio telescope, capable of detecting the equivalent of an airport radar system on a planet orbiting a star tens of light-years away. It will survey the sky continuously, monitoring millions of stars simultaneously. For SETI, the SKA represents a generational step change. Webb and its successors will characterize the atmospheres of dozens to hundreds of potentially habitable exoplanets. If Earth-like planets with biosignature atmospheres are common, if life routinely produces chemical signatures wherever it arises on habitable worlds, Webb's successors should find them within the next few decades to centuries. If they find nothing, if planet after planet shows sterile, abiotic chemistry, that too is a powerful answer. The Mars Sample Return mission will bring samples from Mars's ancient lake beds to Earth for analysis. The result, expected in the 2030s, will either find or convincingly rule out evidence of past life on Mars. If Mars once had life, even 3 billion years ago, the implications for the frequency of life in the universe would be profound. If Mars proves lifeless, despite having been habitable for hundreds of millions of years, the implication runs in the other direction. Either answer will be transformative. The silence, if it continues, is not just a puzzle, it's data. The universe built barriers. Distances that light takes hundreds of millions of years to cross. Speed limits, written into space-time itself. Biological transitions so improbable they may have happened only once. Civilizational vulnerabilities timed almost perfectly to maximize the risk of self-destruction. Dark game-theoretic dynamics that might make silence the only rational choice for any mind that thinks long enough about the cosmos. Whether these barriers are absolute or conditional, whether they are behind us or ahead, whether they've filtered others, or whether they await us, these are questions that the next generation of telescopes, the next generation of SETI searches, the next generation of astrobiological investigation may finally begin to answer. Enrico Fermi asked, "Where is everybody?" in the summer of 1950, and the universe responded with silence. We've been standing in that silence ever since, listening harder with better instruments, thinking more carefully with more data, and arriving again and again at the same empty sky. It remains the most important question we've never answered. And the universe, so far, is not talking. To understand the Fermi Paradox completely, you need to understand one more set of ideas. What researchers have proposed about what very advanced civilizations actually look like, and why their absence is the sharpest constraint of all. The physicist Freeman Dyson proposed in 1960 that a sufficiently advanced civilization would eventually require more energy than its home planet could collect from its star, and would accordingly build structures to capture a larger fraction of the star's total output. The most extreme version, a Dyson sphere, would completely enclose a star, capturing all of its radiation. A star surrounded by such a structure would appear dimmer at visible wavelengths, with the captured energy re-radiated as waste heat in the infrared. Searches for anomalous infrared sources in stellar catalogues have looked for exactly this signature in thousands of stars. None have produced convincing candidates. Soviet astronomer Nikolai Kardashev proposed in 1964 a scale for categorizing civilizations by their energy use. A Type 1 civilization uses all the energy available on its home planet. A Type 2 uses all the energy of its home star. A Type 3 uses all the energy of its home galaxy. Humanity is currently somewhere around Type 0.7. We haven't reached even Type 1. A Type 3 civilization would be visible at intergalactic distances. Its existence would produce unmistakable signatures across multiple wavelength bands. A 2015 study, using data from NASA's Wide Field Infrared Survey Explorer, examined roughly 100,000 galaxies for evidence of large-scale stellar energy harvesting and found no convincing candidates. 100,000 galaxies, each containing hundreds of billions of stars, and nothing resembling advanced engineering. Either such civilizations don't exist, or they are extraordinarily rare, or they have not pursued the energy harvesting strategies that would make them visible to our telescopes. All three possibilities are extraordinary in their different ways. There is another concept that makes the silence particularly hard to explain: the self-replicating interstellar probe, named for the mathematician John von Neumann, who developed the theory of self-replicating automata in the 1940s. The concept is straightforward. A civilization builds a robotic spacecraft carrying artificial intelligence and the ability to mine raw materials from asteroids or other bodies, and, critically, the ability to build copies of itself from those raw materials. Such a probe arrives in a new star system, locates resources, builds several copies of itself, and sends those copies to the next star systems. The copies arrive, repeat the process, and the wave of probes spreads through the galaxy. A probe traveling at even 10% of the speed of light could reach every star in the Milky Way within about 10 million years. On the 13.8 billion year timescale of the universe, 10 million years is a negligible fraction, less than 1,000th of 1% of cosmic history. This means that any civilization that developed self-replicating probes even a billion years ago should, by now, have reached every star system in the galaxy, including ours. The probes would be here. We would find them. In the asteroid belt, on the moon, around the sun. We have not found anything like this. The absence of von Neumann probes is in some ways the sharpest empirical constraint on the Fermi paradox. It doesn't require any specific theory about life's frequency or civilizational longevity. It simply notes that the physics of self-replication and the timescales involved mean that any civilization that achieved this capability, at any point in the last billion years, should have produced probes that are currently in our solar system, and no such probes have been found. The strongest conclusion most researchers draw is the same one Fermi implied with his question. Civilizations capable of building such probes either don't exist, or they don't build them, or something prevents them from spreading. All three options require explanation. The Great Filter concept provides one framework, but the brutality of the mathematics, that any civilization with this capability would fill the galaxy in a geological eye blink, makes the silence especially hard to explain away. Beyond the physical constraints, there is a set of biological ones that deserve serious attention. Specifically, the question of how life on Earth actually got to where it is, and what that timeline implies about other worlds. Earth formed approximately 4.6 billion years ago. The first several hundred million years were extraordinarily violent, the late heavy bombardment, during which Earth's surface was pounded by asteroids and comets at a rate far higher than anything seen in the past several billion years. Some impacts were large enough to potentially vaporize the oceans entirely, and yet, the oldest potential evidence for life on Earth dates to approximately 3.5 to 3.8 billion years ago, meaning that life appeared either during or immediately after the tail end of the bombardment, within a few 100 million years of conditions becoming remotely suitable for it, perhaps within 100 million years. This speed of abiogenesis is one of the most contested data points in astrobiology. Some researchers interpret it as evidence that life arises quickly, given the right conditions. Others point out that we have only one example, and that we are inevitably observing a world on which life did arise. The fact that we exist here means we could only ever be looking at a case where life succeeded, which tells us nothing about how often it fails. What is clear is that once life appeared on Earth, it remained simple for an extraordinarily long time. The transition from simple prokaryotic cells to complex eukaryotic cells, cells with nuclei, with mitochondria, with organized internal structure, occurred approximately 2 billion years ago. The prevailing theory, developed most completely by biologist Lynn Margulis in the 1960s, proposes that eukaryotic cells originated when one prokaryote was engulfed by another and established a permanent internal relationship. The mitochondria inside your cells are the descendants of ancient bacteria that entered into this relationship roughly 2 billion years ago. This event took approximately 1.5 billion years to happen after life's first appearance. 1.5 billion years of prokaryotic life before the first eukaryote. And this transition, from simple to complex cell, is widely considered one of the most significant thresholds in evolutionary history, and potentially one of the most difficult to cross. Once eukaryotes appeared, complex multicellular life still took another 1.5 billion years to develop. The Cambrian explosion, with its extraordinary diversification of animal body plans, came roughly 538 million years ago. Animals with hard shells, eyes, jointed limbs, and bilateral symmetry appeared in a geological eye blink of roughly 10 to 20 million years. From the Cambrian explosion to us took about 538 million years, a long time by human standards, but a relatively short fraction of Earth's 4.6 billion year history. The dinosaurs ruled for 165 million years without ever producing technology. The entire history of the genus Homo covers only about 2 to 3 million years. The emergence of Homo sapiens is only about 300,000 years old. If you compress Earth's 4.6 billion year history into a single calendar year, life appears in February and stays microbial for roughly 8 months. Complex cells appear in July. Multicellular life appears in November. The extinction of the dinosaurs happens around December 26. Homo sapiens appear around 11 p.m. on December 31st. All of recorded human civilization happens in the last 10 seconds of that year. The universe is old enough that if life appeared elsewhere with anything like Earth's timeline, civilizations that formed billions of years before us would now be, by analogy, unimaginably far ahead. And yet, silence. This is perhaps the most viscerally puzzling version of Fermi's question. Not just where is everybody, but where are all the ancient ones, the civilizations that should have had billions of years of head start? The possible answers are the same answers we've already explored. They died, they're hiding, the distances prevent contact. Or they never reached our level in the first place, because the transition from simple life to technological civilization is so improbable that even 13.8 billion years of cosmic history hasn't produced it very often. Maybe, by some calculations, just once. The history of humanity's wondering about this question stretches back millennia. The ancient Greeks debated whether the Earth was unique. The Epicureans argued on philosophical grounds that the universe was infinite and must contain countless worlds similar to ours. The Greek philosopher Metrodorus of Chios, a student of Democritus, wrote in the 4th century BCE, "To consider the Earth the only populated world in infinite space is as absurd as to assert that in an entire field sown with millet, only one grain will grow." This is, remarkably, essentially the same probabilistic argument that drives the modern Fermi paradox. Giordano Bruno, an Italian philosopher who lived from 1548 to 1600, took the logic of the Copernican astronomy further than anyone of his era. Bruno argued not just that the Earth revolved around the Sun, but that the Sun was simply one of an infinite number of stars, each potentially surrounded by inhabited planets. He lectured and wrote about the plurality of worlds across Europe, and was eventually tried by the Inquisition on multiple charges of heresy. On February 17, 1600, he was burned at the stake in Rome. His views on the plurality of worlds were among the charges against him. By the 17th and 18th centuries, the question had moved from heresy to acceptable speculation. Christian Huygens, the Dutch astronomer who discovered Saturn's moon Titan in 1655, wrote a book arguing at length that the other planets of the solar system and the stars beyond were inhabited by beings similar to, though perhaps physically different from, humans. The 19th century brought the first serious attempts to use telescopes to search for signs of life on other worlds, primarily Mars. The Martian canals, described by Italian astronomer Giovanni Schiaparelli in 1877 and popularized by American astronomer Percival Lowell at the end of the century, were optical illusions, straight lines seen by eager eyes in the smeared telescopic images of a planet 56 to 401 million kilometers away. Lowell built an observatory in Arizona dedicated largely to the study of Mars, and wrote 3 books arguing that Mars was inhabited by an advanced civilization struggling against the desiccation of their planet by constructing a global network of irrigation canals. His books were widely read and deeply influential in popular culture, even as professional astronomers grew increasingly skeptical. The disappointment of Mars, the progressive realization through the 20th century that it was cold, thin-atmosphered, and apparently lifeless, was one of the formative episodes in the history of the search for life, and it taught the scientific community an important lesson about the seductiveness of wishful interpretation and the importance of rigorous methodology. The Fermi Paradox has 2 deeply unsettling resolutions, and neither is comfortable. Resolution 1. We are alone. The great filter lies behind us. The origin of life, or the development of complex cells, or the evolution of multicellularity, or the emergence of technological intelligence. One or more of these steps is so improbable that it has happened only once in the observable universe's history, and we are the result. Every piece of music ever written, every work of art, every moment of human understanding, every act of love, all of it is the only such thing in a universe 93 billion light-years across. Not merely rare, unique. The weight of that, if true, is almost impossible to hold. It would mean that the universe's capacity for self-reflection, for wonder, for the asking of questions, resides entirely here, in this one species, on this one planet, orbiting this one ordinary star, in an outer arm of an ordinary galaxy. And it can be lost, all of it, permanently and irrecoverably, if we fail to survive what we've built. Resolution 2. Others exist, but something stops them. The filter lies ahead. The silence is a warning, written across 13.8 billion years of cosmic history, about what happens to civilizations that reach our level of technological capability. Something, nuclear weapons, climate collapse, engineered pathogens, misaligned artificial intelligence, or some combination of the above, destroys civilizations at our stage of development, reliably, nearly universally. The galaxy that should be full of voices is quiet because the voices keep silencing themselves. Under Resolution 2, the stakes of getting our current moment right are not merely civilizational, they are cosmic. The Fermi Paradox becomes not a puzzle to be solved, but a test to be passed, the most consequential test in the history of life. Both resolutions demand something from us, a level of collective seriousness, of long-term thinking, of willingness to prioritize the survival of human civilization over immediate and local concerns that our species has not yet demonstrated at scale. Enrico Fermi understood this, sitting at that lunch table in the summer of 1950. He had built the weapons, he had seen the bomb, he knew what "where is everybody" might mean if the answer was "they were here and then they weren't." The question has never left us, and the universe's silence, patient, vast, ancient beyond comprehension, continues to wait for our answer. There are 2 trillion galaxies out there. Somewhere between them, one man's lunch table question is still echoing, still waiting, still unanswered. And the universe, so far, is not talking. Let's go deeper into the specific physics of what makes contact so difficult, because the numbers are even more brutal than most people realize. The inverse square law governs how radio signals weaken with distance. A signal broadcast at a given power level loses strength with the square of the distance. Double the distance, and the signal arrives at 1/4 the strength, 10 times the distance, and it's 1/100th as powerful. At interstellar distances, even signals that begin at enormous power levels dwindle to levels barely distinguishable from background noise. Our own accidental radio leakage, the radar pulses, television broadcasts, and communication signals we've been generating since the mid-20th century, forms an expanding bubble roughly 100 light-years in radius. But those signals, by the time they reach even the nearest stars, are extraordinarily faint. The television broadcasts we've been sending into space since the 1940s would be essentially undetectable by any radio telescope we could currently build, even at the distance of our nearest stellar neighbors. Our civilization's radio fingerprint is detectable only in the immediate cosmic vicinity, and only by a civilization with substantially better technology than we currently possess. This raises a critical point about the search. SETI is effectively looking for deliberate beacons, signals specifically designed to be detected across interstellar distances, broadcast with enormous power, and probably directed towards specific candidate star systems. An accidental radio leak from a civilization at our current technological level would be essentially invisible at interstellar distances. The search is predicated on the assumption that some civilizations intentionally want to be found and invest significant energy in making themselves findable. Is that a reasonable assumption? Frank Drake himself pointed out the possibility that advanced civilizations might have transitioned away from broadcast radio entirely, that our own civilization might be heading in that direction, as fiber optics and targeted satellite communication increasingly replace wideband broadcast radio, making Earth quieter to an outside observer even as our technological sophistication increases. If civilizations routinely transition through a brief radio window of a century or two before moving to communication methods that are less detectable from outside, the chance of catching that window during our own brief window of listening is low. The radio spectrum is enormous, spanning from extremely low frequencies of a few hertz to frequencies in the terahertz range. Any given SETI search can only monitor a subset of that spectrum at any given time, and the assumption that another civilization would broadcast near the hydrogen line frequency of 1420 MHz is a reasonable hypothesis, but not a certainty. We are searching an enormous haystack with relatively limited tools, looking for a needle whose characteristics we don't actually know. And the timing constraint makes everything harder. A radio signal exists in the data stream of a telescope only during the time the telescope is pointed at the right star, in the right frequency channel, at the right moment. If a civilization broadcasts for 1 second per year toward our star system, on a specific frequency, we'd need to be pointing our telescope at their star, tuned to their frequency, during that 1 second. The probability of that coincidence is very low for any individual star being monitored. The wow signal illustrates this exactly. If it came from a real source that has been transmitting continuously ever since, why has no other telescope in nearly 50 years detected it again? The answer might be that no other telescope has been pointing in exactly the right direction, at exactly the right frequency, during a period when the source was transmitting in that direction. If the signal is directional, aimed in a specific direction that sweeps through the sky like a lighthouse beam, the window during which it passes through any given telescope's field of view would be brief and potentially separated by long intervals. The mathematical consequence of all these constraints is that even in a galaxy reasonably full of radio signals, a search covering a tiny fraction of those stars at a given moment would expect 0 detections most of the time. The current silence is consistent with a range of scenarios, from "the galaxy is nearly empty of civilizations" to "the galaxy is full of civilizations but we haven't looked in the right places with the right instruments yet." One SETI researcher, Jill Tarter, has compared the search conducted so far to filling an ordinary bathtub with water from Earth's oceans and checking that water for signs of fish. If you found no fish in the bathtub, you wouldn't conclude the oceans have no fish. You'd conclude that you've searched a tiny sample. The square kilometer array will compress the search space dramatically. Its combination of sensitivity, sky coverage, and simultaneous multi-frequency monitoring will cover more stars at higher sensitivity than all previous SETI programs combined. A null result from a completed SCAR SETI survey would be considerably more informative than the current null result. A detection would obviously be more informative still. There is one more resolution to the Fermi Paradox that deserves serious consideration before we close, because it's simultaneously the most hopeful and the most disorienting. The possibility that the silence is not real, but rather that we don't speak the language. The assumption underlying every SETI search that has ever been conducted is that we know what a signal from another civilization would look like. We assume it would be electromagnetic radiation. We assume it would be in frequency ranges accessible to radio telescopes. We assume it would contain structured patterns that our signal processing algorithms would recognize as artificial. These assumptions are grounded in the only example we have, our own civilization, and they might be profoundly wrong. A civilization that has been technological for 1,000,000 years has had time to develop forms of communication that are, by our current standards, as far beyond radio waves as fiber optic broadband is beyond smoke signals. They might communicate using quantum entanglement effects we don't fully understand. They might use modulated neutrino beams, which pass through all matter without absorption, and which we currently have no practical ability to generate or detect in a directed fashion. They might use gravitational wave pulses, which propagate at the speed of light and are not absorbed by matter. They might use something outside any physics we currently know, and the history of physics is a history of discovering that there was more than we knew. Under this interpretation, the galaxy might be alive with communication, saturated with signals in every direction, and we walk through it every day, seeing only silence. Not because the signals aren't there, but because we're looking with the wrong instruments, at the wrong frequencies, for the wrong patterns, using the wrong conceptual framework to recognize what we'd see, even if we found it. This is the most optimistic reading of the silence, and it's also the most humbling. It suggests that the real barrier to contact may not be distance or death or rarity, but simply that we are new here, very young, still learning to read the universe's vocabulary. We have had radio telescopes for 60 years, in a universe that is 13.8 billion years old. We have surveyed a tiny fraction of the sky, at a tiny range of frequencies, at a tiny level of sensitivity. We have been asking the question seriously, with scientific instruments, for less than 0.01% of cosmic history. In that context, the silence might not mean absence. It might just mean we haven't been listening long enough, or well enough, or in the right way, and the universe has been patient, as universes tend to be, waiting for us to figure that out. Let's also dwell on what Fermi's question means in human terms, because it matters that this wasn't a question posed in a laboratory or a journal article. It was blurted across a lunch table by a man who had spent the preceding decade helping humanity build weapons capable of ending itself. Enrico Fermi was born in Rome in 1901 and demonstrated mathematical intuition that colleagues described as superhuman. He won the Nobel Prize in Physics in 1938 and emigrated to the United States that same year, escaping the fascist laws that had spread to Italy. On December 2, 1942, in a converted squash court under the stands of Stagg Field at the University of Chicago, Fermi and his team achieved the first self-sustaining artificial nuclear chain reaction. A coded message was sent to Washington. The Italian navigator has just landed in the New World. From Chicago, Fermi went to Los Alamos to work on the Manhattan Project. He was present for the Trinity test on July 16, 1945, the first detonation of an atomic device in the New Mexico desert. In his characteristic style, he dropped small pieces of paper from his hand as the shockwave arrived, measured how far they scattered, and calculated the yield of the explosion on the spot. Roughly 10 kilotons. The actual yield was about 18 to 19 kilotons. His estimate was close enough. This was the man who, 5 years later, asked, "Where is everybody?" The context matters. Fermi had spent the preceding decade building weapons of mass destruction. He had helped create tools capable of destroying cities. By 1950, the Soviet Union had detonated its own atomic bomb in August 1949, less than 4 years after Trinity. The Cold War arms race had begun. The men at that lunch table in Los Alamos understood, better than almost anyone on Earth, what it meant for a civilization to acquire the ability to destroy itself. When Fermi asked his question, the people around that table weren't wondering abstractly about alien life. They were physicists who had personally participated in the development of weapons that, if deployed at scale, could silence Earth the way the rest of the cosmos appeared to be silent. The joke that produced the laughter wasn't really a joke. It was recognition, the kind that hits somewhere behind the chest. Fermi died of stomach cancer in November 1954, at the age of 53. He was still working on theoretical physics in the months before his death. His colleagues described him as the last physicist who had complete command of both theoretical and experimental physics, a breadth of mastery that became essentially impossible to achieve as the field expanded after World War II. Richard Feynman described Fermi's estimation method, the ability to get surprisingly accurate answers to seemingly impossible questions using only basic reasoning and order of magnitude calculation, as something close to a superpower. Where is everybody? Was, in that sense, a classic Fermi question. Strip the problem down to its bones, make the estimates, and see what the math says. What the math said disturbed him, and it has disturbed everyone who has thought carefully about it since. Here is what we know, distilled to its essence. The universe is 13.8 billion years old. It contains approximately 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. Most stars appear to have planets. Roughly 1 in 5 Sun-like stars has an Earth-sized planet in its habitable zone. There are perhaps 40 billion such planets in our galaxy alone. Life appeared on Earth within a few 100 million years of conditions becoming suitable. Complex life appeared after about 3.5 billion years. Technological civilization appeared after about 4.5 billion years. The Milky Way is old enough that civilizations arising 4 billion years before us could have colonized every star in the galaxy and still had time to spare. Self-replicating probes, traveling at 10% of the speed of light, could saturate the galaxy in 10 million years. A Type 3 civilization harnessing a galaxy's full energy output would be visible from intergalactic distances. None of this has been observed. No signal, no probe, no megastructure, no visitor. The universe presents an enormous potential and an impenetrable silence. The explanations are roughly, life is far rarer than the numbers suggest, or civilizations destroy themselves before they spread, or civilizations exist but hide, or the barriers of physics make contact impossible despite everyone's existence, or something about our detection methods means we're looking in the wrong way at the right universe. Every one of these explanations requires either that something is deeply unusual about Earth, or that something is deeply dangerous about the developmental stage we're currently in, or that the universe is structured in a way that makes contact effectively impossible regardless of how many minds exist within it. None of these is a comfortable answer. All of them are serious. And perhaps that's the most important thing to take away from Fermi's question. Not any specific answer, but the seriousness of it. This is not a puzzle for science fiction conventions or late-night speculation. This is a question about the nature of existence in the universe, about whether minds are rare or common, about whether civilizations survive, or whether they carry within them the seeds of their own silence. The universe has had 13.8 billion years to fill itself with voices. The result is quiet. We have had 60 years to listen seriously. The result is one candidate signal, 72 seconds long, never repeated. Those two facts, the vast potential and the actual silence, sit at the center of everything we don't yet understand about our place in the cosmos. Enrico Fermi put it in 5 words at a lunch table in New Mexico, and we've been living inside that question ever since. The universe is not talking. Yet. There's a mathematical argument for taking the Fermi Paradox seriously that doesn't depend on any specific hypothesis about what the great filter is. It starts from a simple observation about what it would mean for us to be alone. The observable universe contains approximately 2 trillion galaxies. Each galaxy contains, on average, roughly 100 billion stars. Working with these rough numbers gives approximately 2 times 10 to the 23rd power stars, 200,000 billion stars, in the observable universe. If you want to argue that Earth hosts the only technological civilization in the observable universe, you are arguing that out of those 200,000 billion star systems, with their associated planets, with the chemistry and physics that appear to be universal, exactly one produced us, and nothing else anywhere produced anything comparable. That is an extremely strong claim. It requires that either the probability of life is so low that even at these numbers the expected count is less than 1, or that some near-universal mechanism destroys civilizations before they reach visibility. The probability of life required to produce a universe empty of other technological civilizations except us. Given these numbers, and a rough estimate that perhaps 1 in 5 sun-like stars might have an Earth-like planet, would need to be on the order of 1 in 10 to the 22nd power, or smaller. That is a number with no intuitive parallel. It is smaller than the probability of picking a specific atom at random from the mass of the Moon. This is not an argument that we are not alone. It is an argument that if we are alone, the improbability involved is so extreme that it demands an explanation at least as dramatic as the improbability itself. Either the chain of events that produced us involves steps of almost incomprehensible rarity, or our current understanding of how life and intelligence develop overstates how likely they are, or the universe has properties that make our existence, specifically and peculiarly, improbable. All 3 of these possibilities are scientifically interesting. All 3 represent enormous challenges to our understanding, and all 3 could, in principle, be investigated through astrobiology, through physics, through the continued development of theoretical frameworks for the origin and evolution of life. The alternative, that others exist but contact is prevented by physics, distance, silence, or catastrophe, is in some ways easier to believe. Not because it's more comfortable, but because it requires fewer extreme improbabilities. If life is reasonably common but contact is impossible or absent for structural reasons, you can maintain a universe in which the probability of life is not absurdly small, while still explaining why Earth has never been visited and our radio telescopes have never received a confirmed signal. The mathematics doesn't tell us which interpretation is correct. What it does is show that the stakes of the question are real. The Fermi Paradox is not a cute puzzle for amateur philosophers. It is a genuine scientific problem with implications for how we understand our place in the universe, the likelihood of our own long-term survival, and the nature of the cosmos itself. One of the most counterintuitive aspects of thinking about the Fermi Paradox is what's called the anthropic selection effect, and it matters because it complicates one of the most natural assumptions we make when we reason about our situation. The anthropic principle, in its weak form, states simply that the universe we observe must be compatible with our existence. This sounds trivial, but it's not. It means that any observation we make of the universe is subject to a selection effect. We can only observe a universe in which observers like us can exist, so the properties we observe are not a random sample of all possible universes, but a biased sample. biased toward those properties that permit our existence. Applied to the Fermi Paradox, anthropic reasoning produces an important constraint. Consider the question of how often abiogenesis occurs. We observe a planet where life arose. We cannot observe a planet where life did not arise, because there are no observers there to make the observation. If we use the fact that life arose on Earth to estimate how often life arises on habitable planets, we need to correct for the fact that we're inevitably observing a case where it did arise. Nick Bostrom, the Oxford philosopher who developed the simulation argument, has been one of the most rigorous thinkers about this. He points out that our existence tells us that life arose at least once in the observable universe, but it doesn't directly tell us how often it arises. If life arises with very low probability, say once per 10 to the 22nd habitable planets, and the universe contains that many habitable planets, then on average, one instance of life arises in the observable universe, and we would be it. Our observation that life exists tells us nothing about whether that probability is large or small, because we can only exist in the rare instances where it happened. This is a genuine epistemological challenge. It means that the fact of our own existence is not as much evidence as it might seem for the abundance of life in the universe. We know life is possible. We're proof of that. We don't know how probable it is, and our existence can't tell us. And it has a specific application to the Great Filter. If the Great Filter is somewhere in our past, if becoming a technological civilization requires passing through a nearly impossible bottleneck, anthropic selection predicts we'd find ourselves on the lucky side of that bottleneck, regardless of how often it allows passage. The fact that we made it through doesn't tell us whether making it through is common or rare. We could be the 1 in a billion success story, and we'd have no direct way to know it from the inside. This is why the discovery of life elsewhere in the universe, on Mars, in Europa's ocean, in the atmospheres of exoplanets, would be so enormously significant, even apart from the direct scientific interest. Each independent origin of life shifts our estimate of how often life arises on habitable planets. If life arose independently on Mars, it means abiogenesis is not astronomically rare. If we find life in Europa's ocean, the case for common life becomes even stronger. And each confirmation that life is common nudges the Great Filter away from the early stages of biology and closer to something between where we are now and the galaxy-colonizing civilization stage. Every data point that moves the filter forward is, from a purely logical standpoint, a data point that makes the ahead-of-us interpretation more likely. And every step toward the filter being ahead is a step toward the most unsettling implication, that something routinely destroys civilizations after they reach our stage of development, and we don't yet know what it is. Consider the history of life on Earth one final time, viewed from the most distant possible perspective. 4.6 billion years ago, a cloud of gas and dust collapsed under its own gravity and formed our solar system. The third planet from the resulting star accumulated rock and ice and began to cool. Within about 500 million years, something remarkable happened. Chemistry organized itself into self-replicating molecules, and then into cells, and the first life appeared in the young ocean of a world still being pounded by asteroids. For the next 3 billion years, nothing much changed. Single-celled organisms colonized the planet, invented photosynthesis, and in doing so, gradually poisoned their own atmosphere with oxygen, which then became the foundation for a new kind of metabolism that would eventually power every animal that ever lived. But for 3 billion years, the most complex thing on Earth was a bacterium. Then, about 600 million years ago, something changed. Complex multicellular organisms appeared. Within a few tens of millions of years, the Cambrian explosion, the major animal body plans all appeared in the fossil record, as though a vault had been opened on biological innovation that had been locked for 3 billion years. Eyes appeared, skeletons, jointed limbs, the architecture of predation and defense. From there to us took 538 million more years. Vertebrates, fish, amphibians, reptiles, dinosaurs, mammals, primates, hominins, Homo sapiens. 300,000 years of anatomically modern humans. 12,000 years of agriculture. 5,000 years of cities and writing. 400 years of modern science. 150 years of radio. 60 years of SETI. The first radio signal we broadcast that could in principle be detected by another civilization left Earth in the mid-20th century, and is currently a sphere about 80 to 100 light-years in radius, expanding at the speed of light. That sphere contains a few thousand stars. Of the hundreds of billions of stars in the Milky Way, we have announced our presence to a fraction of 1%. We are very new at this. We have been capable of interstellar communication for less time than it takes our Sun to travel a single light-year in its orbit around the galactic center. We have been asking Fermi's question with scientific instruments for less than 1/10,000th of the age of the universe. And yet we expect an answer. We are impatient in the way that only very young things can be. The universe has been patient for 13.8 billion years. It will continue to be patient. The question is whether we will be here long enough and listening carefully enough to finally hear a reply, or to understand, through the continued silence, what the silence means. There are 2 trillion galaxies out there. Somewhere between them, 5 words are still echoing from a summer lunch in New Mexico in 1950. But where is everybody? The universe has not yet answered. And the only thing more extraordinary than the silence is the fact that something in the universe is listening for a sound. Let's take stock of what the various proposed solutions to the Fermi Paradox actually demand of us intellectually, because each one, examined carefully, carries assumptions and implications that ripple far beyond the immediate question. The rare Earth solution demands that we accept an enormous coincidence. Every specific condition of Earth, the stable Sun, the large Moon, the plate tectonics, the magnetic field, the Jupiter shield, the galactic address, the specific timing of the Great Oxidation Event, the specific ecological conditions that drove the Cambrian explosion, the specific evolutionary pressures that produced language and cooperation in our hominin ancestors. All of these happened not just on Earth, but in exactly the combination and sequence required to produce us. The rare Earth solution doesn't require each individual condition to be unique. It only requires that their combination is extremely improbable, and the multiplication of individual modest improbabilities across a long chain of required events can produce a final probability that is very small indeed. The great filter ahead solution demands something darker, that the silence we observe is the statistical consequence of civilizations routinely failing to navigate some specific threshold of development. Under this solution, we are currently approaching that threshold, and we don't know what it is. This is perhaps the most motivating version of the paradox. It doesn't just explain the silence, it urges action. If something destroys civilizations at our stage, understanding what that something is and how to avoid it is arguably the most important project in the history of our species. The distance and physics solution demands acceptance of a universe that is simply too large and too bound by the speed of light for civilizations to reach each other. Under this solution, the paradox resolves not through rarity or death, but through isolation. Civilizations may be common, may even be peaceful and long-lived, but the universe's physical structure prevents them from ever making contact. This is in some ways the most peaceful resolution, but it comes at the cost of a deep loneliness that is difficult to fully absorb. Imagine that millions of civilizations exist right now, each one looking up at the same cosmos, each one hearing the same silence, each one as bewildered and as alone as we are. The deliberate silence solution, whether it takes the form of the dark forest theory or the zoo hypothesis or simple inward turning, demands that we accept a universe in which other civilizations have made a conscious choice about us, either to avoid us, to protect us, or to ignore us. Each version of this is disturbing in its own way. Being avoided or protected implies judgment. Someone has evaluated us and found us unready or unworthy of contact. Being ignored implies insignificance on a scale that is difficult to sit with. The wrong instrument solution, the possibility that we're looking in the wrong way with the wrong tools for the wrong kinds of signals, is perhaps the most epistemically humble option. It doesn't require that others are rare or dead or hiding. It only requires that the specific assumptions baked into 60 years of SETI searches are incomplete. This solution is hopeful in one sense and troubling in another. If we can't trust our current detection methods to find what's there, how do we know what to look for next? None of these solutions is obviously correct. None can be ruled out. The Fermi paradox is genuinely open in a way that few scientific questions are, and that openness is itself a kind of answer, an answer about where we are in our understanding and how much remains to be learned. The emotional weight of the Fermi Paradox is worth dwelling on, because it's part of what makes it remarkable as a scientific question. Most scientific puzzles don't carry existential stakes. Whether dark matter is made of WIMPs or axions, whether string theory is correct, whether the Higgs mechanism operates the way the Standard Model predicts. These are important questions, but they don't reach down into the part of you that wonders whether you matter, whether others like you exist, whether the universe is the kind of place that cares whether you're in it. The Fermi Paradox does. At its root it asks, are we alone? And that question resonates at a frequency that no amount of scientific framing can fully muffle, because it connects directly to some of the oldest and deepest needs of human experience: the need for community, for understanding, for the comfort of knowing that others exist who might recognize us. The history of human religion, mythology, and philosophy is in large part a history of answers to this question. Every major religious tradition addresses whether there are other conscious beings in the cosmos, whether there are gods, spirits, ancestors, angels, demons. Every mythology populates the sky with intention. The stars are not just gas and dust and nuclear physics to most human beings across most of human history. They are presences, they are watched, they are watching. Science has stripped much of that intentionality away, and in doing so has made the question of whether others exist both more precise and more lonely. The stars are not watching. The universe is not populated by beings who know we're here, but the question of whether somewhere among those billions of stars are beings as confused and as curious and as frightened and as hopeful as we are, that question remains, and science has not answered it. What science has done is show us the extraordinary improbability of our own existence and the extraordinary scale of the stage on which that existence plays out. 4.5 billion years of geological and biological history, 3 billion years of microbial evolution, 500 million years of animal evolution, a few 100,000 years of human evolution, a few thousand years of civilization, 150 years of radio technology, and here we are, pointing telescopes at the sky and asking whether anyone else is there. The asking is not nothing. In a universe that is mostly empty space and ancient light from sources that no longer exist, the fact that something in the universe is asking questions about the universe is remarkable. Carl Sagan put it this way: we are a way for the cosmos to know itself, whether or not we are alone, whether or not others share in that knowing. The knowing itself is extraordinary. What should we do with all of this? What is the practical consequence of taking the Fermi Paradox seriously? If the great filter is ahead of us, the practical consequence is clear. Whatever it is, we need to find it and avoid it. Nuclear weapons are an obvious candidate for part of the filter. We've been managing the risk of nuclear exchange for nearly 80 years, with partial success. The weapons still exist, in numbers still sufficient to cause catastrophic global harm, in geopolitical contexts that are less stable than they were during the Cold War's paradoxically predictable mutual deterrence. Climate change is a slower filter, but a real one. The disruption of global agricultural systems, the displacement of hundreds of millions of people, the intensification of resource conflicts, the destabilization of political institutions. Engineered pathogens represent a newer and growing risk as biotechnology becomes more accessible. Misaligned artificial intelligence is a risk that barely existed a decade ago, and whose severity over the coming decades is genuinely uncertain. All of these are risks that our civilization is actively creating, sustaining, or insufficiently managing. The Fermi Paradox, if its darkest interpretation is correct, suggests that civilizations at our stage routinely fail to navigate these risks, and that the silence around us is their epitaph. That's not a reason for despair, it's a reason for urgency. A problem that has a history of killing people who face it is a problem worth taking very seriously. If the great filter is behind us, if we are genuinely rare, the only technological civilization in the observable universe, the practical consequence is a different kind of urgency. We would be the universe's only self-aware presence, the only thing in 93 billion light-years of space that wonders, that creates, that asks questions about the cosmos it inhabits, that imposes a responsibility to survive, to persist, to eventually spread beyond this one fragile planet, and ensure that the experiment of conscious intelligence continues. Not because we are important in any cosmic hierarchy, but because in the absence of anyone else, we are the only custodians of whatever meaning consciousness has in a universe that otherwise has none. Either way, the Fermi Paradox points in the same direction. The situation we are in is more serious than we tend to treat it. Whether the silence is a warning or a responsibility, it asks something of us that our civilization has not yet fully risen to meet. Fermi asked his question in the summer of 1950. He died 4 years later, at 53, of stomach cancer, still working. He never knew what his lunchtime remark would become, how it would spark a field, generate careers and conferences and spacecraft and debates, and remain unanswered 3/4 of a century later. The universe that produced him, and that produced the question, and that has so far refused to answer it, is 13.8 billion years old. It has been making stars and planets, and the raw material of life, for almost all of that time. Whether it has been making minds, other than this one improbable exception on this one improbable world, remains the question. And the universe, so far, is not talking. Before we leave this question, it's worth spending some time with the specific moment in history we occupy, because the timing of when humanity is asking the Fermi Paradox is itself significant. We are, right now, in the first generation of humans who have actual data about planets around other stars. Before 1995, when Mayer and Queloz confirmed the first exoplanet, the existence of other worlds was a reasonable inference, but an unconfirmed one. For all of human history before 1995, for all of the ancient Greek philosophers, all of the medieval astronomers, all of the Enlightenment scientists, all of Fermi's generation, the question of whether other stars had planets was genuinely unanswered. They were extrapolating. We are not. We are in the first generation to know, from direct observational evidence, that the galaxy is full of planets, that Earth-sized planets in habitable zones are common, that the raw material of life, complex organic molecules, exists throughout interstellar space. That water, the solvent of life on Earth, exists on moons in our own solar system, in the atmospheres of comets, in the ice of asteroids. We are in the generation that will launch the missions to Europa and Enceladus. We are in the generation that operates the James Webb Space Telescope. We are in the generation that will analyze the first samples returned from ancient Martian lake beds. We may also be in the generation that makes the first confirmed detection of life beyond Earth. Not certainly, but possibly. The next few decades will be characterized by the kind of observational capability that would allow, under favorable circumstances, the detection of biosignatures in the atmospheres of nearby exoplanets. Whether that detection comes, or whether it doesn't, we will have more information about the distribution of life in the universe in 2050 than we do today, and more again in 2100. Against the backdrop of 13.8 billion years of cosmic history and 4.6 billion years of Earth's history, the few decades between Fermi's question and its potential resolution is a remarkable compression of time. Fermi asked it in 1950. We may have a meaningful answer within a century of his asking. In the context of cosmic time, that's essentially instantaneous. The question and the answer arriving at almost the same moment on the universal timescale. That compression reflects how fast technology moves once a civilization gets going. In 1950, no exoplanets had been confirmed. No DNA structure had been solved. That came in 1953. No space mission had ever left Earth. Sputnik launched in 1957. No human had set foot on the moon. That came in 1969. The entire history of space exploration, exoplanet astronomy, molecular biology, SETI, and the James Webb Space Telescope all fits within a single human lifetime. Whatever comes next, a detection, a continued silence, a new method of search that changes the terms of the question entirely, it will arrive faster than any previous generation would have expected. The universe has been silent for 13.8 billion years. The first civilization to listen seriously has been listening for about 60. The next 60 years will tell us more than the previous 13.8 billion. That asymmetry between the silence of cosmic history and the speed of technological investigation is one of the most striking features of the moment we're in. We didn't choose to be born into this moment, but we are in it, and the question is ours to pursue. One final thought. The Fermi Paradox is often presented as a puzzle to be solved, a mystery that will eventually have a definitive answer. Maybe it will, but it's also possible that the paradox is less a puzzle and more a permanent condition of conscious existence in this kind of universe. If civilizations are rare, each one will be alone, looking at an empty sky, developing its own answers to Fermi's question, never knowing whether they're right. If civilizations are common but isolated by physics, each one will be alone in a different sense, surrounded by voices it can never hear, sending messages that will never arrive in time. If civilizations exist but hide, each one will be alone in yet another sense, not for lack of company, but for lack of trust. If civilizations destroy themselves, they will be alone briefly and then silent. In every scenario, the experience of being a technological civilization, the specific experience of looking up and asking, "Is anyone there?" and hearing nothing, is essentially the same. The silence that greets Fermi's question may be universal, not because the universe is empty, but because the universe is structured so that every civilization that develops the question is alone with it. That is a strange and beautiful and terrible kind of loneliness. Strange because it might be shared across time and space by millions of minds who can never compare notes. Beautiful because the asking of the question is itself a form of reaching out, of refusing to accept the isolation as final, of insisting that the silence must mean something and that the something must be findable. Terrible because the silence gives nothing back. Enrico Fermi died not knowing the answer. Carl Sagan died not knowing the answer. Frank Drake, who wrote the equation and then spent 6 decades waiting, died in September 2022 at the age of 92, still not knowing the answer. We don't know it either. Not yet. But we are asking, louder and more carefully and with better instruments than any previous generation. And somewhere in those 2 trillion galaxies, across those billions of habitable worlds, in the 13.8 billion years of cosmic history that preceded this moment, maybe someone else was asking too. Maybe they still are. And maybe, in some direction we haven't pointed our telescopes yet, at some frequency we haven't thought to monitor, in some pattern our algorithms haven't learned to recognize. The answer is already there, waiting for us to develop ears good enough to hear it. The universe is not talking, but we have not yet learned to listen. The Kepler Space Telescope, before it exhausted its fuel and went silent in 2018, left behind a catalogue of discoveries that permanently changed how we think about the universe's potential for life. Among its findings was a planet designated Kepler 452b, a world roughly 60% larger than Earth, orbiting a sun-like star at a distance very similar to Earth's orbital distance, with an orbital period of 385 days. The star, Kepler 452, is about 1.5 billion years older than our Sun. Kepler 452b has therefore been in its habitable zone for longer than Earth has existed. We know almost nothing else about it. We don't know if it has an atmosphere. We don't know its surface temperature. We don't know if it has water. We can't see it directly. It was detected only by the faint dimming of its star's light as it passed in front of that star from Kepler's viewpoint. It is a shadow of a world 1,400 light-years away, a statistical inference from a tiny brightness variation in a long series of photometric measurements. But it exists, and it has been there, in its habitable zone, for 6 billion years. While Earth was forming, while life appeared and stayed single-celled for 3 billion years, while the Cambrian explosion reorganized animal life, while the dinosaurs rose and fell, while mammals diversified and primates appeared and hominins walked and Homo sapiens spread across every continent and built every civilization that has ever existed, Kepler 452b was there, orbiting its star, warmed by its light, for 6 billion years. What happened on Kepler 452b in those 6 billion years, we don't know. We may never know, at 1,400 light-years of distance. Even with the James Webb Space Telescope, Kepler 452b is not a practical target for atmospheric characterization. The light from it is too faint, the transits too infrequent and too shallow for the kind of spectroscopic analysis Webb performs. But its existence is a statement. It says, there are places out there that have been habitable for longer than Earth has existed. Whatever the Drake equation's true output, whatever the correct answer to Fermi's question, the universe has been offering these opportunities for a very long time. Whether anything has taken them, whether anything evolved in the waters of Kepler 452b, whether something looked up at its sun 3 billion years ago and began to wonder, whether something built something, whether something asked a question across the silence and heard nothing back, that we do not know. The silence extends to Kepler 452b, and to all the other worlds like it, and to the worlds we haven't catalogued, and the stars we haven't surveyed, and the galaxies we can barely see at the edge of our observable universe. The silence is everywhere, in every direction, at every distance, at every frequency we've learned to listen on. And in that silence, on this one small world orbiting this one ordinary star, in this one spiral arm of this one galaxy among 2 trillion, one species has woken up enough to notice the silence and to find it strange, to expect something different, to refuse to accept the quiet as a final answer. That refusal, that insistence that the universe should not be this quiet, that something should answer, that Fermi's question deserves a reply, is perhaps the most distinctly human thing about the Fermi Paradox. It is not just a scientific puzzle. It is an expression of the kind of species we are, one that looks at the vastness around it and doesn't feel small, but curious, one that looks at the silence and hears not absence, but a question waiting to be answered. Enrico Fermi asked it at a lunch table in the summer of 1950. We're still asking it. Every radio telescope pointed at the sky is still asking it. Every spectroscopic analysis of an exoplanet atmosphere is still asking it. Every mission to Mars and Europa and Enceladus is still asking it. The universe is not talking, not yet, but we are listening, and that, in a cosmos of 10 sextillion stars and 13.8 billion years of silence, might be the most extraordinary thing of all. Think about what it took to produce the moment we're in, the specific moment in which one species on one planet has developed the tools and the knowledge and the curiosity to ask Fermi's question with any scientific rigor at all. It took 13.8 billion years of cosmic evolution, the formation and death of countless stars, the gradual enrichment of the interstellar medium with heavy elements, the formation of our solar system from a collapsing cloud of gas and dust. It took 4.6 billion years of Earth's geological history, the differentiation of the planet's interior, the development of plate tectonics, the formation of the oceans, the establishment of the magnetic field. It took nearly 4 billion years of biological evolution, the origin of life, the invention of photosynthesis, the great oxidation event, the development of eukaryotic cells, the emergence of multicellular life. It took 538 million years of animal evolution, from the first mobile creatures with eyes and nervous systems to every vertebrate, amphibian, reptile, mammal, and primate that has ever lived. It took about 6 million years of hominin evolution, from the first bipedal ancestors of our lineage to modern humans. It took about 5,000 years of civilization, the development of writing, mathematics, astronomy, physics. It took about 400 years of modern science, from Galileo and Newton to Einstein and Drake. It took about 150 years of electromagnetic technology, from Maxwell's equations to radio telescopes. All of that, the entire 13.8 billion year chain of events, every supernova, every geological upheaval, every evolutionary innovation, every cultural achievement, produced exactly this, a species with radio telescopes, asking where everybody is. That chain of causation is either a miracle of cosmic proportions or a demonstration that the universe routinely produces this kind of thing, in which case the silence is the real mystery. There is no middle ground. Either we are extraordinarily rare or extraordinarily isolated. Either way, the situation we find ourselves in, alone with Fermi's question and no answer, is one of the most remarkable situations any mind has ever been in. But the response to that situation matters, not just scientifically, not just philosophically, but practically. Because if we are alone, our continued existence is the universe's only shot at understanding itself, and everything that threatens that existence is a threat to something of cosmic value. And if we are not alone but isolated, then the challenge of surviving long enough and becoming wise enough to eventually bridge those vast distances, or at least to make contact across them, requires exactly the kind of civilizational development that we have so far only partially achieved. Either way, alone or isolated, the Fermi Paradox is not an invitation to despair. It is an invitation to seriousness, to take our existence seriously enough to protect it, to take the question seriously enough to keep asking it with better tools and better methods and more resources than we've devoted to it so far, to take the silence seriously enough to understand that it might be telling us something we urgently need to know. Fermi blurted 5 words at a lunch table and changed the way his colleagues thought about the afternoon. Those 5 words have now been echoing for 3/4 of a century, through thousands of papers and conferences and missions and searches. They will keep echoing until we find the answer, or until the silence teaches us something we weren't expecting. The universe is not talking. But in 2 trillion galaxies, across 10 sextillion stars, around 40 billion potentially habitable planets in our galaxy alone, the question hangs there, patient and enormous and unanswered. Where is everybody? We're still waiting. The universe will eventually answer, not through choice or intention, because the universe has neither, but through the sheer accumulation of evidence that the next generations of science will provide. The James Webb Space Telescope is already gathering atmospheric data from exoplanets that no instrument has ever reached before. The Square-Kilometre Array, when fully deployed, will listen to more stars simultaneously than all previous SETI programs combined. The Mars Sample Return mission will bring back the first samples from the ancient lake beds where water once flowed, and where, if Mars ever had life, the chemical traces of that life might still be preserved in the rock. The missions to Europa and Enceladus will directly sample the most promising potentially habitable environments in the solar system. Within the lifetimes of people alive today, we will likely know more about the distribution of life in the universe than all of previous human history combined. That accumulation of knowledge won't resolve every question. Science rarely gives clean final answers, but it will move the probability estimates, narrow the uncertainties, and bring us closer to understanding what Fermi's silence actually means. The answer might be that life is everywhere, and we've simply been looking in the wrong way. It might be that life is common, but complex life is rare. It might be that complex life is common, but technological civilization is rare. It might be that civilizations regularly arise and regularly fall before they can make their presence known across the vast distances of the cosmos. The answer might be something we haven't thought of yet, a resolution that requires the same kind of framework shift that special relativity brought to the ether paradox, that explains the silence in a way that none of our current theories anticipate. Whatever the answer is, finding it will be one of the defining intellectual achievements of our civilization. And in the meantime, while we wait and search and listen, the question itself does something valuable. It keeps us honest about our smallness in a very large universe, and keeps alive the recognition that our existence here, on this planet, at this moment in cosmic history, is either extraordinarily rare or extraordinarily fortunate, and probably both. Enrico Fermi asked it first, or at least put it plainest. But every person who has looked up at the night sky and felt the silence pressing back is part of the same long asking. The telescopes are just the formal version of something that has been in us since we first looked up. The universe is patient. It has been here for 13.8 billion years, and it will be here long after us. The silence it offers us is not cruel. It is simply what a very large and very old universe looks like to a very young and very small civilization at the beginning of its search. We are at the beginning. The question is still open, and that, against all odds, is exactly where we should want to be.